Good morning. So I'm gonna continue from the last session where I discussed introduced this code, this is interface code to you, which is called TPLS, the first level set. Just a quick recap. This is diffuse interface code that solves Cahn-Hilliard equation and able to solve all kind of multi-phase problems with or without phase change, and specifically in a very high resolution and 3D configuration. And so last session I have already discussed things, so I'm just going to go through a little bit. So we have in TPLS this main source files where each file corresponds to each solver, like Cahn-Hilliard solver for the Cahn-Hilliard equation, and momentum solver U, V, W for now the momentum equation in X, Y, and Z direction. Then you have two-phase initialization to initialize the domain with all the variables. The pressure solver for pressure, temperature solver for the energy equation. The main NS hybrid is a main time loop file where you call every solver and basically the main code. And so today I'm gonna a little bit discuss about this file, which is called Vapor. So let's just go to droplet evaporation. So what is happening here is you have a droplet in the domain and it's evaporating, and the droplet is placed on a heated surface. So yeah, the droplet is placed on a heated surface. So in the surrounding, we have the gaseous mixture where you have the inert gas and as well as the vapor of the liquid that is evaporating. So you have two vapor components here. And you have the liquid. So Cl is the volume fraction, or say liquid volume fraction. If Cl is 1, it's liquid. If Cl is 0, it's the gaseous mixture. But in the gaseous mixture, we now have another volume fraction that we have defined here as Cv. This Cv denotes the volume fraction of the vapor in the gaseous mixture. So if the value of Cv is 1, that means there is only water vapor present in the mixture. Or if it's 0, that means there is only inert gas present in the gaseous mixture. Now this arrows denotes the droplet is evaporating, and m dot is the rate of phase change. That is a mass of the liquid that is converting into vapor. Now, how do we define this phase change? It's a diffusion limited evaporation model, which is very simple, where you calculate the mass flux that is converting from liquid to vapor with the difference of concentration, or in this case, the vapor fraction at saturated state and in the gaseous mixture. So with the help of this formulation, you can calculate how much mass is evaporating from liquid to vapor. And the Cv saturation does also change with temperature, since we have a heated surface. And we also solve the energy equation. So the Cv saturation is a function of temperature, and the very famous equation called Anton equation you can use to calculate the Cv saturation as the temperature changes. So with this evaporation flux, we'll have evaporation cooling, which is quite important. We'll see in the equations now. And another important point to be noted is that in the simulation, we have set on the interface of the droplet where any values where volume fraction is more than 0.9, is to be saturated with the vapor. Okay? So the volume fraction of vapor for any values which is at the interface that is more than 0.9 for liquid volume fraction, we have considered as saturated state. So now, since we have looked at the different variables, now I'll just come into the equations once again because so here we have the continuity equation, but since we have an evaporation now, we have the m dot term here, and here you can see the definition of the density, how density is varying in the domain with CL, the liquid volume fraction, as well as CV, the vapor volume fraction. So in our whole domain, we have now three components: liquid, vapor, and inert gas. And so all the properties, just like density, are function of both CL and CV in the domain that is used in the simulation. Okay. So then we have the momentum equation. Quite general. This the only term that I'm gonna elaborate is this term, which attributes to the thermal Marangoni. So due to evaporation and evaporative cooling, we'll have a surface tension gradient, which generates a tangential component of surface tension. So apart from the normal component, we include the tangential component here in the surface force. So to introduce the thermal Marangoni effects. Next, we have the Cahn-Hilliard equation itself. So it's for the liquid volume fraction CL with the source term with m dot. So since the liquid is evaporating, the mass is transferring from liquid side to the vapor side. It's negative. The sign of the source term is negative. Okay? Now we'll come to the vapor equation. So it's very important here now because of evaporation, now your vapor concentration is changing in the gaseous mixture. So this equation solves basically the advection diffusion of the vapor phase, the volume fraction of vapor, CV, and also the source term m dot. Now, in energy equation, we'll also have evaporative cooling. So there is in energy equation we have this source term as well, and all of these are non-dimensionalized. So you have these non-dimensional numbers: Smith number, Jacobs number, Weber number, Bond number, Rode number, and Pendle number. So just a brief about the boundary condition again. So it's a droplet placed on a heated surface. So the bottom surface is at some temperature, Ts, and the top is at some temperature, and the rest of it is at a bulk temperature, Tv. So in X and Y phases in the domain, we have all used, all of the parameters have periodic boundary condition, but for the bottom and the top, we have the judicial boundary condition. Yeah. So if you see for the Navier-Stokes, and so if you remember, all of these boundary conditions are defined and in the file called PECCRC that is located in the source and setup file itself, where you can mention any kind of boundary condition here for each variable. And also you define the size of your domain with global dimension X, global dimension Z. You select the phenomena in the code that, since you're doing evaporation, with evaporation here. And this liquid and gaseous limit just to define the area in between where the phase changes happen. And all other similar to, like, as mentioned here, Z, it's X and Y upper and lower defines all the boundary conditions for all the parameters in the fetch CRC file. Yeah. So now I think this is the very basic for the evaporation part of the code. I think you all saw the initialized droplet last week, I guess, in ParaView. So I think it'll be easier now if we kind of do hands-on-hands, load some files in ParaView and see the evaporation, see the cooling that is happening due to evaporation on the interface of the droplet. And I have some files already sent to Mayank. You will have an initial file and you will have a file after some time when the little bit of the droplet is evaporated. You can see the comparison and how phase change is happening, and also you can we can go through the code as well for some, like, let's say, to see where the vapor file is and how the vapor phase is solved. So Mayank, so this is it from my side for presentation. I think I kept a bit more time for the hands-on session with ParaView to look at the droplets. It will be easier, and also look through the code a bit, navigate into the files.
Yes, so we can move to the lab, I think. So
yes, yes, so we can kind of do the so yes.
Yeah.
Okay. So is my screen visible?
Yes.
Yeah. Okay. So let's start. So Ken, I think you have all the data files. The data files that it should be something called. Sorry, a second. Oh, just check the name of the folder that has been shared with you. Yes. Do you have this folder called data files, Kian? Maybe Mayank can help. Mayank, can you navigate to that folder?
Data files, Jan.
Yes.
Yeah, we have it.
Yeah, so basically in that you have a few data files. You have a few data files which is ran up to 20,000 time steps after the start of the simulation. And it's a single droplet placed on a heated surface that is evaporating. What you can do is you can open the ParaView that I'm gonna tell you how to visualize the evaporation, the interfacial temperature, and all the other thing that is happening from the simulation. And then after you kind of get a hands on it, then I'll a little bit go onto the code and one or two more slides. Okay, let's just do that this first. So if you can open your ParaView. And then open files. Select
Yes.
the sorry. Yeah. Mayank, maybe you can give me feedback if it's loaded or not.
Yes, so we are in this folder. Which file is to be loaded?
Yeah, so that's what I'm saying. So in this folder, you will see a bunch of .h5 and XTMF file, as I'll just repeat it. So the data from the simulation is generated and saved in .h5 files. But in order to make it readable in ParaView, we have h5.xdmf files. Now you need to load only the .xdmf files in parallel, and each file corresponds to each variable. Can you see here CLN underscore? So CLN is for the liquid volume fraction, CL. CVN is for the vapor volume fraction that I discussed, which denotes the volume fraction of vapor in the gaseous mixture. And M dot here is nothing but the mass flux from liquid to vapor. And Tn is the temperature, and U and V and Wn are the velocities in each direction, X, Y, and Z. So I would ask you to select CL, CV, M dot, and T. Press Control and click on all those XDMF files. CL, CV, CLN, CVN, M dot, and TN.
Okay, we have selected this.
Yes, and then just open it. Press OK.
Yes, we have opened these files in parallel.
Okay, cool. Then if you just press apply, you'll have something like this.
Yes.
Yeah, right. So now what we're going to do is we want to visualize the temperature and the mass transfer on the droplet interface, for which we need to combine these data. Okay. So what we're going to do is just again in this tree, select, press Control and select all the files.
Okay.
Then if you can see in the top panel, there is filters. In filters, if you put search, you'll have a search bar here. Then you can search a filter called append attributes. If you just type first few letters, it will come.
Yes.
Okay. So if you just press enter on append attribute, it's nothing but it's appending all the 4 variables together, so that we can visualize multiple variables on each other.
Okay.
Okay, so now what do we have here? We have the liquid volume fraction, we have the vapor volume fraction, we have the temperature, and we have the m dot, which is the mass flux. So if press apply,
Yes, we have applied it.
and then if you go select on the append attributes, the last part of the tree, select that one.
Okay.
Yeah, now we want to visualize the droplet and the domain, right? So in order to visualize this, first we'll visualize it in 2D in slice to see what is happening in the vapor phase. Then we'll do it by control to see the 3D droplet and how the temperatures on the interface of the droplets are. So if you just take a slice here, in this panel, can you see slice datasets?
Yes.
Just take a slice, press apply. Yes, so then just rotate it in your direction so that you can see the plane.
Yes, we can see.
You can see the plane, right? So now in this panel, you can see since we had different files for each variable, but now we have appended the data. So if you go to this panel here where it's should be like TN selected, if you click on it, you will see all all 4 variables that we are loaded are in this list. Are there in that list? Are you okay?
Yes.
Okay. So let's see, let's check with CL from the definition that we have defined. So if you select first CL, which is nothing complicated. So CL, the red bit is our droplet, which is evaporating, and it's the blue part, CL0 is our vapor. Okay. Now, just go on that list again and select CVN. So we want to visualize the CVN. Okay. CVN is nothing but the vapor concentration or the vapor volume fraction in the gaseous mixture, since we also have vapor. So you can see here, just do not, since inside the droplet it's liquid, so it's always in saturated condition. So any values of CV inside the droplet doesn't matter here. You have to check from like away from the interface in the vapor phase. So you can see here, if this is the interface, and you see there is a gradient of volume fraction of vapor that is reducing
Yes.
from the interface as you go up, which is because firstly, we have set the interface in the saturated condition, as I have mentioned during the presentation, and since it's evaporating, the vapor is also diffusing in the atmosphere. That's how you get this kind of pattern for vapor volume fraction. Now, if you go to TN, it's a bit difficult to visualize from here. We'll see it in 3D because it's you cannot actually see the droplet, but you know. And then M dot here, we will visualize M dot and TN in 3D to make it easier. So now you keep the slice here, or maybe we can delete it. It's better. Just delete the slice. Then go
Okay.
back to the append attributes again. Select it. Just select it. And then if you go to this panel, you'll see a half sphere, which is called
Yes.
contour.
Contour.
Yes. Just select on the contour. And then, in contour, you see contour by. Just select it as CLN because we want to see the interface of the droplet, and for that you need to select the liquid volume fraction. Contour by CLN. And then
Okay, I've selected CLN in contour. So
yeah, so since our interface lies between 0 to 1, so in order to visualize, we'll take a value of volume fraction, let's say 0.5. And then here in the value range, you just put 0.5. Then you apply. You should be seeing something like this, the 3D droplet here.
yes.
So now if we want to see the evaporation, you select, then again, you go to that top bar where you have the list of the parameters. You go and select here M dot. Okay. So now, since this range is too large, you cannot see the evaporation very clearly. So what we'll do is, in the side panel, if you scroll down, can you see this bits here? So from where you put the value range, if you scroll down, then you'll find something called coloring M dot, then edit this rows. Are you able to locate it?
Yes.
Okay. So what we're going to do is just to set the range of M dot values so that we can visualize it a bit better. Because due to the range of these values, it's quite a bit large range, which makes it difficult to visualize. So if you go in this section, the after edit, the third option, you'll see something called rescale to custom range.
Yes.
If you click on it, if you go, let's say we want to see from 0.02 to 0.06.
It is 0.06.
Oh, yes. Wait, sorry. Okay, I think I put the value wrong. So yeah, sorry, just the value. It's a very initial time step, so the evaporation is quite small. So you can see here, if you set the values from, let's say, 0.0001 to 0.04, have you set
Yes.
it? So you
Yeah,
can
yeah.
see the evaporation flux here on from the surface of the droplet. This whiter part are, you can see around 0.02. It's non-dimensional m dot value. And as you go to the apex of the droplet, the evaporation is suppressed. So the evaporation is higher towards the substrate. And as you go on the top, the evaporation is a bit substrate. That is due to the contact angle of the drop and the vapor concentration on air. So it's always, and also we have the temperature on the surface much higher. And so your evaporation is always faster or higher mass flux as you go closer to the substrate, but as you go towards the apex of the droplet, the evaporation is low, which you can clearly see here on top of the droplet. If you see the top view, it will be easier for you to visualize. You can see on the periphery of the droplet, the evaporation fluxes are higher, but at the apex of the droplet, the evaporation fluxes are low.
Yes.
And just see the top view, it will be easier to. And then we see in this panel, if you go, just keep everything same and select TN.
Okay.
Yeah. So if you just take it to Y normal, and then again, we need to reset the range a bit to properly see the gradient on the interface. So if you go to, again, rescale to custom range, if you can find it here in this panel, just stuff in the coloring section, coloring, then TN.
Yes.
So here you can see it's a bit on the higher side. So if we see it from 0.6 to seven. Yeah, I mean, just keep it, I guess, 0.7 is. So if you, oh, sorry. If you keep it from 0.7 to, let's say, 1.1, just keep it 1.2. Yeah, keep it 1.2, 0.7 to 1.2, minimum and maximum. If you keep it, you will see the temperature. Sorry.
No, no, go on. I'm following.
Oh, sorry. So if you see the temperature contour on the on the droplet interface, it also has a gradient because of the evaporation, because of the evaporative cooling. As you saw, the evaporation is a bit faster near the periphery of the droplet. If we go to the top view again, but since our droplet is placed on a surface which is heated, so the temperature on the surface is higher. So the temperature near the contact line will be higher. And as you go towards the apex of the droplet, since it's going away from the surface, the temperature decreases and it's coolest on the apex of the droplet, as you can see here.
Yes. Yes.
Okay. So this is basically due to this change in temperature at the interface, the tangential component of the surface tension force becomes important, which gives you the thermal Marangoni. If you remember, I showed it in our surface force term. So due to the gradient in interfacial temperature, we have change in surface tension. And this surface tension generates an effect called thermal Marangoni, which is also included in our code. You can see it through visualization of streamlines, which is a bit more detailed. So I don't think I have enough time. So are you able to get up to this point?
Yes. Yes.
Okay, cool. So I'll just go back to my slides a bit more to show a few more results that you can use this code to come to. And also I'd suggest just work with the ParaView and the files. Also check the initial files that we loaded last week, and then check these files when the droplet has started to evaporate. And these files are quite big, and so that's why I cannot load so many data files and show you the animation itself, because it might crash the system.
Okay, so it is not possible to load different time steps at the
Yeah,
same time.
yeah, it is possible. It is possible. So in here we have to, let's say we have to see this and the initial state. Then we have to load all the parameters there, and then we append all the data. Then we load it like this. And normally what in our code, what we do is we use a Python script after running the simulation to append all the data and then put it in ParaView, which is a bit complicated for me to explain. Then it will take a lot of time to explain how I'm handling the H5 file. So I'm showing you how to append the data in the ParaView itself. Okay.
Yeah, okay.
Yeah, it's and also these data files are quite large, so I don't know if it can be handled in the lab computers as well if we input like 3 or 4 timestep files in ParaView. So I'll quickly show go back to some of my slides and show what we can do more with the code that you already have in your PCs. So is my screen visible?
Yeah, it is visible.
Yeah, so this is now, as you can see, we have checked the evaporation of a single droplet. Now, this code can be further extended to simulating an array of droplets, which is quite interesting because when there are multiple droplets evaporating, they interact with each other in the vapor phase, creating a lot of vapor in the vicinity, which suppresses the evaporation. So, yeah, so if you see, let's say we have 9 droplets that is evaporating. alongside each other in an array instead of an isolated droplet. You'll see the depletion of the volume of these droplets are different. So some of the droplets deplete or evaporates faster, some of the droplets then in an intermediate range, and the center droplet here is this line, which depletion of the volume is much, much slower. So you can simulate all these kind of scenarios using this code, and you can see very good uh, results for droplet evaporation, and not just 9 droplets. You can simulate hundreds of droplets and see why because of so much vapor due to the evaporation from so many droplets, it in turn suppress the evaporation of many droplets in the center region, which gives you this kind of different slopes for volume depletion. That means different rate of phase change for different droplets in a single array, which makes the difference between an isolated and an isolated evaporation of droplet and then evaporation of droplet arrays. Now you can also visualize it. Let's say I have plotted this. These are the interfacial temperature profile of these droplets that are evaporating. You can see the interfacial interfacial temperature of the droplets are also asymmetric in nature, which comes from this a lot of vapor and then asymmetric evaporation. The cooling is not even across the droplets, which gives you this kind of asymmetric contours for interfacial temperature, which generates, again, as I've said, if there is asymmetry in interfacial temperature, there will be asymmetry in surface tension due to that temperature, which will create different Marangoni effects, Marangoni convection, all those kind of things that you can see here. These are the similar droplets. You can visualize, simulate this currents, convective currents that is going across the periphery. And each droplet in that array shows a different Marangoni convection pattern. As you can see, the corner droplets are like this, and the center droplet is much more symmetric. So this kind of things can also be done with the code, but due to logistics, we cannot like transfer this kind of files and directly show it on ParaView. And so yeah, so this is the capability of the code that it can do. And yeah, so that's it from my side. So if you have any questions regarding the ParaView, regarding the code, please feel free to ask.
Okay, Devashi, it was very interesting, and I guess we will play around a little with this.
Yeah,
So,
play around it a little bit. Look at the code, as I'll just mention. If you go to the code that I haven't shown, so I'll just one more last thing that probably I should mention is just in the code, look at, because there are a lot of files there, which can be a very difficult to understand. Just look at the vapor file and the two-phase initialization file, because the vapor file is very important, because where we do solve the vapor equation, vapor volume fraction, and also the phase change term m dot, where we calculate it using the expression that I've shown in the presentation before. Okay, and also play around with the ParaView, see the mass transfer and temperature and different initial state. Yeah, thank you, and please let me know if you have any question that I can clarify. Mayank here, you can email me as well.
yes, so I don't think there are any questions right now.
Okay, cool. Thank you. Thank you
Okay,
for.
Devashi. Bye.